Okay, let's continue our example now with a linear fit. Okay, and let's build this example on this nonlinear fitting exercise, where we found that this logistic function is a good candidate for this specific data set with an average error of 0.56 something. Okay, and we are going to use the very same data set now for a linear curve fitting. So let's remember first the linear curve fitting. In this case, we are using a line function. So it is something like y is equal to mx plus b. And in this case, m and b are the ones that we are looking for. For the line fitting, we are lucky. We don't need to search. There is an analytical solution. Okay, so there is a solution. We can just compute it with one shot. We already derived this formula, so let's represent the unknowns, this linear fit parameters, with a beta vector. Inside we have these unknown parameters m and b, where m is the slope of the linear fit and b is the point where it crosses the y-axis. So first we need to fill a capital X matrix which consists of lots of ones in the first column, okay, and as a second column we have this controlled variables. So the first element of x vector, second element, this is small x, are controlled variables, and we have n of them. Okay, so our capital X matrix at the end has n rows and 2 columns. And similarly we have a y vector that consists of the dependent variables 1 all the way down to n. Okay, so this one has n rows and 1 columns. So, and this unknown beta matrix is given by x transpose times x, okay, and we get the inverse of this, and we're going to multiply this by, again, x transpose, and we multiply it with y transpose. So this will directly give us the best line parameters. So let's do this with MATLAB. So I can basically clean this part. Let's keep the fprintf part here. Okay. So first I'm gonna clear everything, or I'm gonna close all the windows. Okay. And I redraw my figure. Okay, so I made a typo, I have to correct it. So let's rerun this part, and I get the very same figure. And now I define a capital X. Okay, so let's look at my workspace. My workspace now has an element with 1 rows and 17 columns, so I have to transpose this first. Okay, my capital X matrix consists of ones with a size of X transpose, so that it is a column. It represents a column, and similarly the second column is the X transpose itself. So let's try this out. And now the X has 17 rows and 2 columns. Very good. This is what I wanted. So I have to define also the capital Y in a similar way. It just includes the dependent variables. Okay, now all I need to do is to plug this formula in to compute my beta. Okay, beta is capital X transpose times capital X and inverse of this guy times X transpose times Y. Let's evaluate these. And now we get two beta values. First one is the point where it crosses the line, y-axis, and the second one is the slope of the fit. So let's now calculate Y best line model. That is beta's second element, which is m, right? So beta's second element is m times this x, which is our independent variables, plus beta 1. Okay, so since beta is scalar, it doesn't matter if I dot multiply or just multiply this, but let's keep the dot multiply. It doesn't matter at all. So when I run this now, in my workspace I have one best line model and one original Y. And now I'm going to compute the average error for the line. So what did I do? I had to use a sum inside which I have an absolute value, the difference between Y and Y best line model, and at the end I divided this by the length of Y. Okay, now I get the average line error. So now I'm ready to report. So the best line function, best line, I don't need to call it a function, best line has these parameters. Slope is this, and B is this, with an average error of blah blah. So now we need to provide these numbers. So slope is the second element of beta, right? And this is the point where it crosses the y-axis, and then I have the average error. Okay, save. So all is missing is a nice plot. So I have to hold on, then I can plot X versus Y best line model. Now I'm going to use a blue color. Okay, I'm ready to run. Plot the run button, and this is what I get. So this is pretty much an okay fit with an error of 0.77. Apparently, if you remember the previous example, this error is bigger than the error of the logistic function, which means the logistic function is a better choice for this example.